Have you ever paused to think about how you remember anything at all? From your best friend's birthday to that tricky math formula, our ability to recall information is fundamental to who we are. But how does the brain actually turn experiences and facts into lasting memories? It's a complex, incredible process, and at the heart of it lies a small but mighty brain structure, the hippocampus. Today, we're going on a journey deep inside your brain to demystify memory formation, focusing on this crucial region. Get ready to understand one of the most vital functions of your brain. Our brain is an incredibly complex organ, constantly processing information. Different regions specialize in different tasks, from sight and sound to movement and emotion. Memory isn't stored in one single spot like a file cabinet. Instead, it's a distributed process involving several brain areas working in concert. However, there's one region that acts like the orchestrator, especially for new memories, the hippocampus. It's truly fascinating how this small structure integrates vast amounts of information to create coherent recollections. So, where exactly is the hippocampus? Imagine a seahorse. Now, imagine a structure deep within your brain's temporal lobe, shaped much like that seahorse. That's your hippocampus. You actually have two of them, one in each hemisphere of your brain. It's part of the limbic system, a group of structures involved in emotion, motivation, and, crucially, memory. For decades, scientists knew it was important, but its exact role in shaping our understanding of the world through memory wasn't fully grasped until a groundbreaking case. To truly understand the hippocampus's importance, we must talk about patient H.M. or Henry Molaison. In 1953, H.M. underwent experimental brain surgery to treat severe epilepsy. The surgery removed parts of his temporal lobe, including both hippocampi. While it helped his epilepsy, it had a profound and tragic side effect. H.M. could no longer form new long-term declarative memories. He could remember things from before his surgery, but couldn't recall new faces, events, or facts just moments after they occurred. His case was a monumental breakthrough in neuroscience. H.M.'s case revealed a crucial distinction: our memory isn't just one big thing. He couldn't form new declarative memories, facts and events, but he could still learn new motor skills, like tracing a star while looking in a mirror. This suggested that different types of memory exist and are handled by different brain systems. This led scientists to distinguish between two major memory systems: declarative memory and non-declarative memory. It was a paradigm shift, proving the hippocampus was essential for specific memory types, but not all of them. Let's break down these two main systems. Declarative memory, also known as explicit memory, is about knowing what. It's the memory of facts and events that you can consciously recall and describe. This is where the hippocampus shines. Non-declarative memory, or implicit memory, is about knowing how. These are memories you don't consciously access, like riding a bike or the unconscious skill of typing. H.M.'s ability to learn new skills despite his severe amnesia perfectly illustrated this critical difference. Within declarative memory, we have two primary subtypes. First, there's episodic memory. This is your memory for specific events and experiences, like remembering your last birthday party, what you ate for dinner yesterday, or your first day of school. It's tied to a specific time and place. Second, there's semantic memory. This is your memory for facts, concepts, and general knowledge, such as knowing that Paris is the capital of France, the definition of photosynthesis, or the rules of chess. These memories are generally not tied to a specific learning event. Now that we know what kind of memories the hippocampus handles, let's explore how they're actually formed. Memory formation is generally broken down into three crucial steps: encoding, consolidation, and retrieval. Think of it like creating and saving a file on a computer. First, you type the information in, encoding. Then, you save it, consolidation. Finally, when you need it, you open the file, retrieval. The hippocampus plays a starring role in the first two stages, especially for new declarative memories. The first step, encoding, is all about getting information into your brain. When you experience something new, whether it's hearing a new name, seeing a new face, or learning a new concept, your brain takes in that sensory information. The hippocampus is vital here because it acts as a hub, integrating information from various sensory regions. It processes the what, where, and when of an experience, essentially creating a preliminary record. This initial processing is critical. Without good encoding, there's nothing to consolidate or retrieve later. During encoding, the hippocampus doesn't just receive information, it actively binds together different aspects of an experience. Think about remembering a specific party. The hippocampus helps link the music you heard, the faces you saw, the conversations you had, and the smell of the food into a coherent memory. It's like compiling all the separate ingredients into a recipe. Without the hippocampus's binding function, you might remember individual elements, but you wouldn't be able to recall the event as a complete, unified experience. This integration is a hallmark of its role. How does the brain actually store this information? It comes down to something called synaptic plasticity. Our brains are made of billions of neurons, and these neurons communicate across tiny gaps called synapses. Synaptic plasticity refers to the ability of these synapses to strengthen or weaken over time in response to activity. When neurons frequently communicate, their connection gets stronger, making it easier for them to communicate in the future. This physical change at the synaptic level is the biological basis for learning and memory. One of the most important forms of synaptic plasticity is long-term potentiation, or LTP. This is essentially the persistent strengthening of synapses based on recent patterns of activity. When a specific neural pathway is repeatedly activated, say, when you're trying to remember a new fact, the synapses along that pathway become more efficient. They're more likely to fire together in the future, forming a stronger memory trace. The hippocampus is a prime location for LTP, making it crucial for the initial formation of those enduring connections that underlie new memories. Once information is encoded, the next critical step is consolidation. This is the process where newly acquired, fragile memories are stabilized and transformed into more enduring, long-term forms. Imagine writing something down on a sticky note. It's there, but it could easily get lost. Consolidation is like transferring that information into a sturdy notebook. This process can take hours, days, or even longer, and it's heavily influenced by factors like sleep. The hippocampus is essential for this initial stabilization of memories, helping to replay and reinforce the neural patterns. Sleep plays a surprisingly active and vital role in memory consolidation. While you're sleeping, your brain isn't just resting, it's busily working to replay and reinforce the neural activity patterns that occurred during your waking hours. This replay happens particularly in the hippocampus, which reactivates memories and facilitates their transfer to other brain regions for long-term storage. So, pulling an all-nighter before a test might feel productive, but getting enough quality sleep is actually crucial for truly cementing that information in your memory. What exactly is a memory once it's consolidated? Scientists refer to the physical and biochemical changes in the brain that represent a specific memory as an engram, or a memory trace. It's not a single neuron or a single location, but rather a distributed network of neurons and their synaptic connections that are strengthened and modified during encoding and consolidation. The hippocampus helps to establish this initial engram, acting as a temporary index or pointer to all the scattered elements of a new memory in various cortical areas. For new declarative memories, the hippocampus acts like a temporary index or librarian. When you learn something new, different parts of that memory, the sights, sounds, emotions, are processed and stored in various areas of your cerebral cortex. The hippocampus's job is to link all these disparate pieces together, essentially creating a pointer to where each fragment of the memory resides. It's not storing the full memory itself, but rather the instructions on how to access and reconstruct it. This indexing role is crucial for initial recall. Over time, through a process known as systems consolidation, the memories that initially relied on the hippocampus are gradually transferred to the cerebral cortex for more permanent, long-term storage. This is why HM could remember events from before his surgery. Those memories had already been consolidated and stored in his cortex. The hippocampus essentially teaches the cortex how to reconstruct the memory independently. Once fully consolidated in the cortex, the memory no longer relies on the hippocampus for retrieval. It's like the librarian passing off the complete file to the main archive. The final step in our memory journey is retrieval, the process of accessing and bringing memories back into conscious awareness. When a memory is newly formed and still reliant on the hippocampus helps reassemble all the scattered components from the cortex. Once memories are fully consolidated in the cortex, retrieval can happen directly from there. This is why some memories, like childhood events, can feel so vivid and easily recalled, even without an active hippocampus, because they've made their permanent home in the cortex. It's important to note that memory isn't a static, unchanging recording. Every time you retrieve a memory, it becomes temporarily vulnerable to change. This process is called reconsolidation. When you recall a memory, it's briefly reactivated and then needs to be restabilized. During this window, the memory can be updated, strengthened, or even weakened based on new information or experiences. This constant editing means our memories are living, dynamic constructs, not perfect recordings, which is a mind-blowing concept in itself. So there you have it, the incredible journey of memory formation, with the hippocampus as our central guide. From encoding new experiences by binding disparate sensory information, to consolidating them through synaptic plasticity and long-term potentiation, and finally acting as a temporary index before memories migrate to the cerebral cortex for permanent storage. This tiny seahorse-shaped structure truly holds the key to our ability to learn, to grow, and to remember who we are. It's a testament to the brain's astonishing complexity and adaptability. Keep learning, keep exploring, and keep forming those amazing memories.